Got a couple proofs to talk out here. It's kind of medium hard here. Start to the left. I've already written in the premises here. I think it's reasonable abbreviation. Just make an arrow below the word premise for justification. What we have, premise 1, not x and y. Secondly, we have if not e, then in parentheses, y if and only if u. We have x or if z, then not e. And what we're trying to prove is one of two things. We either have this whole expression in brackets, if z, then y if and only if u, or not u. Alright, with proofs you definitely want to think about how you can proceed to prove new things as well as where you're going. As we saw in the last section, you really need to think about both things, sort of working forward and working backward here. In this particular proof, we notice this is an or conclusion. So two things ought to come to mind, two ways we can get an or claim. I mean, this whole entire claim doesn't appear here. It's related, but it's a fair bit different than anything in the premises. So barring that, we are either going to use the rule that allows us, the two rules that allow us to derive, one of the two rules that allow us to derive an or claim. We can use addition rule, right, where we have P and then we just go to P or Q. Or we have the constructive dilemma rule, which I'm going to jot down briefly here, where we have an or statement, P or Q, and then we have a conjunction of if-thens. As we saw in the last clip, in this section, we get either R or S out of that. Those are the two things going to lead us backwards towards this. Okay, U doesn't appear in here at all, so we pretty much know this is going to be use of addition rule to get, first we're going to have to prove the expression in brackets, and we're just going to add on with addition or not U. How we can get that expression in brackets? Looking backwards here, if z, then y if and only if u. That's an if-then. Think about rules that allow us to prove if-thens. And hypothetical syllogism is the only rule that does that. Of course, the if-then again could appear in here, but it doesn't. We look towards hypothetical syllogism. Okay, scanning what we have in premise 2, we have if not e, then y if and only if u. In premise 3, as a part of it, we have if z, then not e. If we get that second part of line 3, we could set up a hypothetical syllogism. Watch the pen here. If z, then not e. If not e, then y if and only if u. Put those two things together, we can get if z, then y if and only if u. So the question then becomes, can we prove z, if z, then not e? And if we take a look at what we have in lines 1 and 3, we're going to be able to do it. Line 1 is not x and y. We can use simplification to get not x from that. Anytime we have an and, we can use simplification. And then with not x, we got a disjunctive syllogism. We have an or claim in 3. First part of the or is not true, so the second part has to be true. And that's, in a nutshell, pretty lengthy explanation, but the full explanation of how to do this particular problem. Okay. I'm going to get my pen working here. Let's see if that does it. Sorry about that. Okay, so first step, not x. That's a simplification of line 1. Then staring us in the face, perhaps, but of course it's not obvious if you're not familiar with the rules. You need to get familiar with the rules by thinking about them, practicing proofs, and first and foremost, to get started, practice the exercises. Look in the book where you work on what is and is not an instance of disjunctive syllogism, hypothetical syllogism, constructive dilemma, and so looking back at the other rules. What we get from lines 3 and 4 is if z, then not e. And that's a disjunctive syllogism. That rule is applied to lines 3 and 4. Now, if we look at what we have in 5 and what we have in line 2, that fits perfectly for a hypothetical syllogism. Here and elsewhere, if you can't see what's coming, stop the tape, stop this video, and see if you can figure it out first before I write it in. What we get is if z, then y, if and only if u. That's hypothetical syllogism. Lines 2 and 5. And once we have that, for sure at this point we got to look at where we're going with the conclusion. We can just use addition to finish the problem. Addition tells us that when we have some claim, we can say that or anything else that we choose, and that's guaranteed by the addition rule, by how the OR operator works. That's an addition on line 6. Take a look at the next proof. Okay, see if you can solve it before I do it. Here's how we're going to put things together. We actually have an or statement for our conclusion again. This time, it turns out, you want to scan it, see if you can figure this out. It's going to be constructive dilemma. That's going to be the only way to get there. We're not going to be able to prove B. We actually have not B in line 3. Perhaps there could be a contradiction, and in the book it shows you in this section how you can prove anything from a contradiction, and that is an important thing to note. Theoretically, it seems troubling you can prove anything from a contradiction, but it's not so troubling if we point this out. You wouldn't want to affirm a contradiction. Contradictions are nonsense. You're talking out of both sides of your mouth, and it shouldn't be that surprising that you can prove anything from a contradiction. The problem is not with the mechanism of proof. The problem's with the contradiction, what you start with. An argument with contradictory premises that form a contradictory set will always be valid, but it will never be sound. The premises can never all be true by the very nature of them being contradictory. All right, going forward here, perhaps you don't even know how to finish up. That's one way you can proceed. It's not going to take you all the way, but in many proofs, in some cases, it will. Lines 2 and 3, we have a basic modus tollens, so I'm going to go ahead and enter that to begin. We get not A by modus tollens with lines 2 and 3. Okay, now we really got to think for a little bit. But if you look at what we have, line 1 tells us if not B and not A, then A or C. We just proved not A. We already have not B in line 3 as one of our premises. So we can use our conjunction rule to set up a modus ponens, and that's what we need to do to proceed here. Conjunction allows us to form any two claims that we have as true, as premises or things we've proven. With an and claim, a conjunction between the two. So that's a conjunction, lines 3 and 5. And then we can use modus ponens. If you look at lines 1 and 6, they fit together. Modus ponens, let's make this and a little bit more clear here, giving us A or C. So the justification is modus ponens, lines 1 and 6. And at this point, it gets a little bit harder. But you scan what we have quite a bit in 7 lines. Hopefully you will eventually be able to see this. We have a constructive dilemma. We need to set it up, though, to get our conclusion. What we need to do is take line 2, if A then B, and line 4, if C then not D, which we can put those together by conjunction. We can always put any two lines together by conjunction. This is a conjunction of lines 2 and 4, as I said. And now we do have just exactly the form for a constructive dilemma, which is hard anytime we have a constructive dilemma. It's our most complicated rule. But we have A or C. A gets you B, C gets you not D. That tells us that we have either B or not D, and that's the constructive dilemma rule, lines 7 and 8. And there you go. We got a couple pretty high-level proofs with the 8 rules.